Another thing we can do with cryptography is hashing. Hashing is a one-way function, and we only use it for integrity. It does not provide confidentiality, non-repudiation, only integrity. We briefly touched on it earlier when we talked about the compromised hard drive, where we need to make a bit-level copy of it, hash the original, hash the copy. Those hashes will need to match. That would indicate the two drives are identical. Then we do our forensics. We would hash the copy drive again. The forensics was done on the copy drive. All three hashes should match. It doesn't say anything about what's on the drive, just that nothing on the drive changed. For hashing, remember it's a one-way function. You cannot reverse engineer anything from the hash. And that it's a variable length plaintext hashed into a fixed length value hash, or an MD, a message digest. And what that really just means is, it doesn't matter how long the input text, the plaintext you use is, the output hash is always going to be the same length. Variable length plaintext, fixed length value. We use hashing to prove the integrity hasn't changed. Just like we did on a hard drive, it could also be a file we download from the internet. Many sites where you can download software or patches from, it'll show the hash that's supposed to be from the software. You can then download it, hash the software, and see if your hash matches the one they publicized. Obviously, if the site is compromised and the attacker has access to the site, they can change how the hash is supposed to look. In hashing, we talk about collisions. A collision is when the hash of two different sets of data, two sets of plaintext, provide the same hash. It is possible, but it's very, very unlikely. For many years, MD5 or Message Digest 5 was the hashing tool of choice. It produced a 128-bit fixed-length hash. It was very widely used until someone found a flaw in it. You can really cause a collision in any hashing algorithm if you have enough time. Problem is if you can produce it in a reasonable amount of time. Someone found a flaw in the algorithm, they're able to produce a collision in less than a couple of hours. And while it's not a chosen text collision, it is still a collision. Even with this flaw, it's still very widely used. If the original text was send $1 million to this account number, and I was able to change the account number and produce the same hash, that would be a chosen text collision. But regardless of that, it's not desirable, and there are newer hashing algorithms out there that are collision resistant. MD6, a Message Digest 6, was designed to replace MD5, but both SHA-2 and 3 were better. MD6 wasn't used for very long. It was in the running for the SHA-3 race. Just like AES, it was a competition. But during the competition it was withdrawn because it was discovered to have flaws. I haven't seen it used ever, and I think it was only used for a brief amount of time, but just for the exam, know those key facts. What a hash does is it shows us that the file is still the same it was when it was hashed the first time. If I use Charles Dickens' Great Expectations again, the entire first chapter, 1800 words, if I change just a single comma, the hash I get from it is going to be entirely different. Here's you the full text pasted in. I generate a hash. Then I change the last period to a comma. And you can now see the hash is entirely different. And remember, variable length input, fixed length output. So let's look at some more hash functions. So both SHA-1, 2, and 3 are secure hash algorithm 1, 2, and 3. SHA-1 uses a 160-bit hash value, that's the fixed length output. It does have weak collision avoidance, it's still very commonly used. Both SHA-2 and SHA-3 are considered collision resistant, and both SHA-2 and 3 are also somewhat used now. Haval, or hash of variable length, is based on the MD design principles, but it's much faster. And you can choose the output length, 128, 169, 192, 224, or 256 bits. This again is not very widely used. It is, however, considered collision resistant. For the exam, know what hash functions are, what they do, what they don't do, how they work, and then the high levels of each of the types. Many of the other hashing functions we talked about already were developed in either military or government contracts or competitions, and some people have had some concern that there might be backdoors built into them. Because of that, the RIPE-MD and the RIPE-MD 160 were designed. RIPE-MD used 128, 256, or 320-bit hashes. It was not widely used and is no longer considered secure. RIPE-MD 160 was a redesign of RIPE-MD. It uses 160-bit hashes. It is considered secure and collision resistant, but it also is not widely used. Many times when we store passwords on a server, we obviously don't want to store the plaintext password. If an attacker got access to our server, they got all our passwords. What we do instead is we store hashed values of the passwords. If the stored password hash matches the hash of the password I just entered, it must be the same. If the attacker knows which hashing function we use, they can use precompiled rainbow tables. Rainbow table is just a list of hashes, commonly used passwords, but it can be millions of passwords long. So if they get a hold of our hashed password, they can compare the hashed password to the list of passwords they have, and they might very easily be able to gain access to the password. So to counteract that, we use salting and nonces. Salting is random data added as an additional input to the one-way function. So not only do I have my password of Thor is awesome, and even if the salt is just ABC, a hash would show that my password now is Thor is awesome, ABC. The attacker would try that and get a wrong password. Obviously, the salting is much more complex, but you get the idea. Nonces are very similar. The word is just made up from number and ones. It's an arbitrary number that's only used once. If it's often a random or a pseudo-random number used in an authentication protocol to ensure that all communication can be used in replay attacks. We also use nonces as an initialization vector in a hash function. In the example on the right, a client needs to authenticate. It sends a get nonce request to the server. The server sends it a nonce. The client then replies back with a login, which consists of the username, a client nonce, and then the hash of the nonce, the client nonce, and the password. The server then compares all that to its own hashes using the same nonces. If they match, the server grants you a token and allows you to log in. It may seem complicated at first, but just logic through it a few times. Explain each step to yourself. Server does this, client does this, server replies with that. For any certification I do or any studying I do, I talk to myself a lot. I explain things to myself, because if I can explain it, that means I understand it. It takes a little longer, but the results are really great. Try it out and see if it works for you.